The motivation of our work is to generate optimal trajectories in real time. Solving trajectory optimization using direct collocation or shooting method with nonlinear programming is computationally expensive. Efficient methods like minimum snap trajectory generation, which formulates a quadratic programming problem with trajectories represented by piecewise polynomials, does not fully exploit system dynamics. We aim to generate optimal trajectories in real time while taking advantage of system dynamics. We propose a method that is able to generate optimal trajectories in real time. Our method is composed of an offline training stage and an online computation stage. We illustrate our method by generating trajectories for a quadrotor. During the offline stage, we randomly sample 50,000 initial states in the quadrotor state space. We then solve an optimal trajectory generation problem for each initial state, driving them to zero with respect to some objective. We then use a neural network to learn the mapping from initial states to corresponding optimal trajectories. The offline stage stops here. During the online stage, we first predict an optimal trajectory using the neural network trained in the offline stage. Then we use a one-step quadratic programming to refine the predicted trajectory. The figure shows the predicted trajectory, refined trajectory, and the optimal trajectory. As can be seen, the refined trajectory is quite close to the optimal. We demonstrate our method on two tasks. In the first task, we compare trajectories generated by our method and the minimum snap method for point-to-point navigation. The quadrotor has to travel from one point to another within a designated duration. In our experiment, when the duration is set to 2.9 seconds, the tracking controller is not able to follow the trajectory generated by the minimum snap method. The quadrotor crashed due to motor saturation. In contrast, the same tracking controller is able to track the trajectory generated by our method. When the duration is set to more than 3.1 seconds, the tracking controller is able to track trajectories from both methods. However, we can see the tracking error is larger on minimum snap trajectory. In the second task, we demonstrate the real-time capability of our method. The quadrotor has to track a moving target. It will try to stay 1 meter right above the target, which is moved by a human. While pure PID fails when the target moves too fast. In order to find the limit of our method, we try to move the target faster and faster until the quadrotor crashes. We log the movement of the target and replay it using minimum snap method as the trajectory generator. We found that both methods crash about the same time, but our method has a smaller tracking error. In conclusion, we found that mapping from quadrotor states to optimal trajectories can be learned, and the learning process is data efficient. Also, we demonstrated that our method can be applied in real-time tasks. Finally, our method leads to a better tracking performance compared to minimum snap method.